few words. The next speaker is Eva-Maria Hainzl from Technical University in Vienna. And the talk is again about catalytic variables and about universal properties of catalytic variable equations. So,
thank you very much. Thanks for having me here in Pennsylvania. Great to be here. The title of the talk sounds massive, like universal properties of catalytic variable equations. Like I unravel all the mysteries of catalytic variable equations for you right now. Of course, this is not going to happen. I'm sorry. This was sort of a clickbait title, I guess, that we chose. But let's get more specific about what we're actually going to talk about. And actually, the previous talk was a great introduction to mine. So we're going to talk about generating functions with one catalytic variable. So again, catalytic variables mean that the nth coefficients in set of m set u is a polynomial in U. And typically we are interested in the evaluation of m set u at a very specific value of u. So for example, here if we have m set u set marks the number of steps that we would make in a walk in the quarter plane, where we are allowed to make diagonal steps up and diagonal steps down, then you could, for example, mark the height at which we end. And this parameter, this height, is naturally restricted by the number of steps that we do. Yeah. And now m set 1 would be the number of all walks that end in the quarter plane after n steps, and m set 0 would be just the walks that end on the x-axis, for example. So depending on what you're interested in, the x-axis. Example that we've already seen where these catalytic variables come up on math enumeration, where the catalytic variable keeps track of the root phase balance. And we've also already seen functional equations involving these catalytic variables. This, for example, would be the functional equation that you could come up with if you want to describe paths where you're allowed to make diagonal up steps, diagonal down steps, and like steps of of the vector 1, -2, for example. So here we've already seen these divided differences in the last talk, which I will denote just by delta of E set u. And then we also have further divided differences, higher divided differences, that I denote by delta 2, for example. And so sometimes I also refer to them as second discrete derivatives somehow. But I'll try to stick with the notation in the previous talk. So divided differences, second divided difference. Okay. What we can see here is that we have the generating function that we're interested in equals, and then on the right-hand side, we have a polynomial with positive coefficients in set u, d set u, and divided differences somehow. These are technically the catalytic variable equations that we're interested in. Here again, the example of the planar maps, and we've already seen that we can like transform it into this very nice form that we're interested in somehow. So these are the equations that we consider. Now, the universal properties that we're interested in are not something like whether the series is algebraic or definite or whatever, but more like this is based on something that has been observed in the 70s for the first time. That if we have, for example, a functional equation for a generating function in just one variable, for example, here the functional equation for dig paths, then there's a theorem by Bender from 1974 that says that d of z is first of all always an analytic function. If on the right hand side d of z always shows up with a vector of z, then d of z is always analytic around 0. And if you do singularity analysis, you'll always have a square root singularity, always. And this is true not only for polynomials, like because we're talking about algebraic series. This is not true if the right-hand side is a function, as a function is a polynomial, but also for any analytic function with positive coefficients. So it could also be like here, z times the exponential function of d of z or something like that. You'll always end up with the square root singularity. And of course, if you use the transfer theorem, then this would translate to asymptotics that somehow look like constant times n to the minus 3/2, which comes from the square singularity, times r, which is just 1 over the location of the singularity to the n. And you can easily compute these numbers then, of course, like if you need heuristics on the asymptotics of your coefficients, where you would just take this functional equation, you take the partial derivative with respect to d, because if d of z becomes singular, then of course the partial derivative has to become singular, otherwise the implicit function theorem would give us a local analytic extension of the series. So these two equations have to be satisfied. You plug this into the computer and compute, okay, z equals 1 is the smallest set where this is satisfied. And then you'll also notice that z minus 1/2 is also a singularity. So the singularities cancel for n odd, but in general, this is what gives you these asymptotics, kind of asymptotics. Okay, now that we've already talked about maps, let's compare this with the asymptotics for maps. Had computed these in like 68, I think, or something. And they are of the form constant times n to the minus 4/2, 12 to the n. So here we have completely different exponent, even though we know that the functional equation for maps, that the generating function of maps is algebraic. So even though we know that it satisfies the polynomial equation, we know it will never be of this form, where we have nz1 equals, and then we have a polynomial with positive coefficients that would somehow describe this map. So in its nature, it's somehow very different, and this is captured by this characteristic exponent, basically, in the main asymptotics of the coefficients. So now we would think, okay, what if we add a catalytic variable? Maybe we always get this exponent as a characteristic exponent somehow. So especially we're now considering this m of zu equals z times. So this z factor is important because it will guarantee that there's a unique analytic solution for the functional equation. And q, we now assume is polynomial with positive coefficients. Let me mention, we do not need the polynomial. It can also be an analytic function. In the variable zu, mzu, and the divided difference of mzu. And we've already seen decomposition of dig paths, for example, with a catalytic variable. And we know, of course, that dig paths, we've just seen the example before, have this characteristic of exponent minus 3/2, while maps have minus 5/2. So just the appearance of a catalytic variable does not necessarily give us this characteristic exponent. But in 2020, Drmota and Yu proved that there's a dichotomy. If Q is linear in like mzu and delta mzu, and non-degenerate, I'm not going to go into the details what this means, but then you have a 1/2 singularity. And if it's non-linear, like it is in the map case, then you have a 3/2 singularity. Okay. And now I've already shown you also an example where we have higher order divided differences. What happens then? Because technically it's the same concept. So we would expect that this generalizes. And in fact, it does. I will, to some degree, at least when k is 2. But I will go through these ideas, how we compute this result somehow, and then you also see some, well, I guess, universal properties, or like, yes, some universal properties that you can always observe if you do these computations, like in a specific case. And it's based on this general method in this paper that was already cited in the last talk by Mireille Bustamelu and Arnaud Shehan, that appeared in 2006, where they proved that catalytic variable equations yield algebraic solutions, so that mzu is algebraic. They also give this specific method that I will show you in a second, But before I do this, let me just rewrite something. It's really not deep, it's not important, but I don't want to lose you just because I use new variables and I want to save space. So I'm going to rewrite mzu as u times delta mzu plus mz0. And then I'm also going to rewrite q as a polynomial in delta mzu and mz0. Well, yeah, that's this. So this will just help us to save space on the slides. And it's maybe worth mentioning that R is has still positive coefficients. So in some sense, the nature is still very similar to the previous cases. So the general method uses a very simple and beautiful idea somehow. We already know that we have unique analytic solutions. We plug them in, and now around 0, we just differentiate with respect to u, and then this equation has to be satisfied. So maybe let's just have a look at the left side and see whether this is true. mz0 will just disappear if we differentiate because it does not contain a u, and then u times delta mzu will become delta mzu plus u times, and this is how I denote the partial derivative of delta mzu with respect to u. And now the second step is we group terms with the factor of the partial derivative of delta mzu. So on the left-hand side, this is u, on the right-hand side, this is z times r by 0. I left out the coefficients here, space. And if they add up to 0, then of course the rest of the terms, the magenta terms, also have to add up to 0. And for this particular equation here, where we only have u equals something, we can use the Spender theorem that we've already seen. You know, like we have u equals z times, and then here we have a polynomial. In this case, could also be an analytic function with positive coefficients. We know it has a unique analytic solutions with certain properties. We even know that you will have a square root singularity. Right from here, this is handed to us. So this function exists, and then we can evaluate that mzu along the solution, and we basically get 3 equations in 3 indeterminants then. So where d of z now is evaluation of delta mzu along this u of z, and mz0 is just abbreviated for mz0. And now we have like an equation system that we can analyze. If everything is analytic around 0, everything is nice, we can use standard tools, and this is how you can obtain the result by Drmota and me. But now we want to consider higher order derivatives, and like basically we use the same method as before. We plug in the analytic solutions, we differentiate, we group the factors. Again, we have these 3 equations, but now the second equation basically, and this is also shown in this paper by Bustamante and Shehan, that this equation now has 2 solutions. And in our case, it actually has always 2 distinct solutions. This is somewhat important because if we evaluate delta mzu then along these 2 both solutions, then basically we generate 6 equations for 6 indeterminants. But let us maybe first have a look at the solutions to this, what I call the curve equation. And I plotted them somehow as like real algebraic curves somehow. And the thing is, usually when you when you compute them and you get this Puget expansion around 0 for these solutions, it usually starts with z to the 1/2. So it's not analytic around 0, which is why it's it's not so nice if you want to do analytic combinatorics in singularity analysis. But still, it's not really a problem, because we can express these solutions as g of z plus minus square root of h of z, where g of z and h of z are analytic functions around 0 with positive coefficients. And we can see that this u1 of z, it's always monotone increasing, of course, it's always positive along the positive wheels. And this u2 of z, the absolute value of u1 of z is always larger than the absolute value of u2 of z. And this is something that we can prove in general if you have higher discrete, higher order divided differences somehow, then you would have u to the k and k different solutions, but there will always be one U1 of Z that will be real, the absolute value will be larger than all of these others. And the nice thing about this U1 of Z is the largest solution somehow to this equation. And I'll show you a rescatter plot of the C here. What it actually does is it leads to the boundary. So this is just the real numbers somehow. And this magenta curve here marks the boundary of convergence of MZU. So if Z becomes this large, then basically MU Z0 or MZ0 both become singular somehow. So this is in general like the boundary of convergence at this point, but also for smaller Z, U could become larger, and this would then be the boundary somehow. And the solutions to this equation somehow, it comes from 0, and then U of 1 leads you exactly to this boundary of convergence, joins this boundary of convergence, and yeah, actually shows here. And here we will actually do this this singularity analysis. And what's also like easy to see here is that U2 will actually not contribute to the singular behavior of M1 and of MU Z0 and MZ0. The functions that we're actually interested in. So U1 is like the important thing. Okay, so let's again, I already mentioned we're going to evaluate delta 2 and ZU along these two solutions, and then we plug these into our 3 equations, and basically we end up with 6 equations. And now to find the point, the singularity, again, we would look at the partial derivative of the single equation, but now of course we look at the Jacobian of the system, and the determinant of the Jacobian has to be 0. Otherwise, again, implicit function theorem would give us extensions. And the determinant, so this Jacobian actually has a very nice form. If you write it down like this, it's a block matrix of 2 times 2 matrices. So the determinant factors into the determinants of A, B1, and B2. And I'll show you a plot how these determinants usually behave. Yellow is the determinant of A, blue is the determinant of B1, and the determinant of B2 is here red. And you can see the only determinant that is really important that becomes 0 is the blue one, the one B1 that is related to the functions U1 and D1, which is just MZU evaluated along U1. So here you can also see like this will give us the singularity somehow. And then I can also show you the values of the functions U1, U2, D1, and D2. Blue is U1, and we can see, okay, this looks very much like this curve that I've shown you before, where we join the boundary of convergence of MZU. Then we have D1, which also makes a similar curve somehow, and D1 and U2 that look very uninteresting somehow in this case. Okay, so what I will not prove here, but what we proved in paper is that only the determinant of D1 is relevant for determining the singularity. U1 will have this, will show this dominant type alpha, the type of the singularity of alpha. And it will translate to this singularity in the nonlinear case will translate to a 1 plus alpha singularity for MZ0 and MU Z0. In the linear case, the singularity translates directly. So MZ2 and MU Z0 will have also an alpha singularity. And usually alpha is just 1/2. But we would need this equation to be satisfied, which looks very complicated and whatever, but it's not obvious that it's not satisfied because we have this -6 here. Otherwise, we would have a 1/3 singularity. But first of all, this has never been observed in the wild. And second of all, we also cannot generate numerically somehow an example where this would happen. But still, if you look at the value of this equation, then this is also very typical. It starts basically at infinity, and then it becomes very small, and it can become arbitrarily small somehow. So it's not always obvious that it's not 0. So somehow makes sense to check somehow. But yeah, so in general, we can say if we have just a second order discrete derivative, then we always have a free-half singularity in case this equation is satisfied and the Q is nonlinear. And if Q is linear, then we immediately get the one-half singularity from this U1. That's it, sorry. Yeah.
So I have a question, if you can hear me. So
Yes.
in a long time ago, Gifayol, Maleshev, and others analyzed that kind of equation using Hilbert-Riemann boundary problem. And they were getting basically how to compute this M0 or N0G or whatever. There was a way to do it. I'm not sure how it is related to this. Could you comment about this if you know something about it?
I don't know anything about this, but Michael also doesn't know anything about this apparently.
No, I don't know.
No, but we're happy if you could send us a reference.
So basically, as I understand, because of analyticity, if you have well-defined M0, MGU, this somehow define MG0 and M0U. And using this, look at it at some point, Hilbert-Riemann boundary problem, if I remember. And they were actually getting a result that seems to be similar, but I don't remember it. It was in queuing, two-dimensional queuing.
Oh, interesting. Okay, thank you.
Thank you.
Is there other questions online or
Oh, there is a question.
no?
Marie has a question to Wojtek.
No, I think we should ask a question to the speaker. I can chat with Wojtek later.
Fine. I see.
Okay.
Okay, so I have one question. So you just consider the two-dimensional, so the case where k is equal to 2. What do you think about a bigger k? So k.
Yeah. So
Are you optimistic? Do you think that you can extend your method, or I don't know?
Yes and no. I mean, we think it definitely should hold for any k, but at the moment, so when I showed you that the determinant of P1 is the only determinant that is relevant, we cannot show that this is the case for general k, and then things become complicated. This is where we have this problem, and it's based on the fact that we can express U1 in terms of G and H somehow. If we have more solutions, then maybe we would need to express it as a combination of G1, G2, G3, or something like several functions. And then it's not so easy to show anymore that only B1 is the relevant determinant. This is the main problem at the moment. Yeah. But technically, it generalizes, and also, well, if you want to do it computationally, you can just check k more equations. And if they're satisfied, then it's fine. Then you also get the same result.
Other question? Online? Is there any more questions? No? So, okay. So, thank you.
Okay, so